Hello guys, and good day to all of you. So now we meet again. Okay, so welcome to chapter 3 of gas power cycle for the last part of this chapter for the part 4. So basically in these sessions we will discuss on the method that we use to increase the efficiency of this particular engine. Right. So basically, one of the famous method, we call it the Brighton cycle with the regeneration. Yeah? So basically, as you can see in the graph now, in the slide now, okay. So we still have the basic component, which is a compressor, combustion chamber, and turbine. But in this case, the hot gases from the turbine has been channeled into the regenerator, and then this hot gas basically will include in the system and entering before entering the turbine. Okay, so in the gas turbine engine, the temperature of the exhaust gas leaving the turbine is often considerably higher than temperature and leaving the compressor. So this one can be proved by looking at the TS diagram. Okay, and then therefore the high pressure air leaving the compressor can be heated by the hot gases that come out from the turbine by using a counter fluid exchanger, what we call it regenerator or a recuperator. The thermal efficiency of Brighton cycle will be increased as a result of this method, because when you preheating the gases that come out from the compressor, so that the temperature drop is not very significant. So they have some temperature drop, but it's not as lower as the temperature at the leaving of the compressor. So that's why the value of heat addition will be reduced. And then so this ratio basically we call it regeneration. So the regeneration have the effectiveness before this is effectiveness between the ideal the actual of the Q regeneration divided by the ideal Q regeneration. As you can see here, okay, basically the effectiveness of the regeneration can be represented in terms of this expression. Okay, so here, right? So whereby this one is going to be the Q regen actual, okay, and then this part is going to be Q regen maximum. Okay, so this one, the ratio between Q regen actual with the Q regen maximum will be the effectiveness of the regeneration. So basically this one is equal to m dot Cp, okay, T5 minus T2, okay, and then divide by m dot Cp T5 prime, okay, minus T2. So in this case, T5 prime will equal to T4. So from here, you can see here, here, same. So this one can be cancelled, so that's why we will left you in terms of the temperature. Okay, right? Right. So this is the ideal cycle, but if you have the actual cycle, so obviously we have the actual value lah. Okay, so the actual value here as well as the turbine actual value. So if they have the centropic efficiency for both compressor and turbine. So if they have the value of actual, that means this one is something like this. Okay, so here is T5 prime, and here is going to be your T5 lah. Okay, so the most important thing is that when you heated when you channel the hot gases from the turbine to the regenerator, so that means the value of Q in here, instead of T3 minus T2, is reduced to T3 minus T5. So when you reduce the heat addition, that means the thermal efficiency will be getting improved. So that's theoretically, okay, right. So if you're talking about the actual, when you have the actual cycle, okay, so when you have the actual cycle, that means you have the isentropic efficiency for the compressor as well as the isentropic efficiency for the turbine. So, effectiveness of regeneration will be T5 minus T2 actual divided by T5 prime minus T2 actual. Something like this one. Okay. Whereby the T5 prime is equal to T for actual. Whereby T5 prime will equal to T for actual in this case. Okay. Right. And then the Q in also from T to T5 the Q in. So the value of Q in equal to M dot Cp T3 minus T5. Okay, right? Then when you redirect, okay, rechannel the hot gases from turbine to the regenerator. Okay, that means you can some sort like Q save. So Q save actually is equal to Q generation, which is T4 minus T6 is equal to T5 minus T2 or T2 actual. Okay, right. Then the thermal efficiency for regeneration can be calculated by using this formulation. Can be use this formulation, or you can use the W net over Q in. Okay, right. So this one, okay. The thermal efficiency it depends on the ratio of the minimum and maximum temperature as well. So regeneration is more effective at the lower pressure ratio and low minimum to maximum temperature ratio. You can improve also. You can get the maximum value of thermal efficiency. Okay. So as you can see here in this graph, as you can see when you increase the thermal efficiency, okay, with the regeneration case, okay, the thermal efficiency of the Brayton cycle will getting lower. You can see it's getting lower, but it depends also on the ratio of the T1 minus T3, which is the maximum and minimum temperature. As you are setting a very lower of value of ratio between the T minimum and T maximum, basically generally you will get the higher thermal efficiency as compared with another design point of T minimum and T maximum. And then as you can see here in this graph, basically with regeneration, the trend, okay, the trend of the when you increase the pressure ratio, the thermal efficiency will getting decreased for the regeneration, but it will contrast with the without regeneration. Okay, so without regeneration, as you increase the thermal efficiency, generally you will get the increment also for the thermal efficiency. Okay, right? So you increase the pressure ratio, that means you also increase the thermal efficiency for the Brayton cycle. So basically, this is for regeneration. So these are two different things. So basically, when you have regeneration, that means you doesn't require for the high pressure ratio of the compressor, right? Very besar. If it doesn't have regeneration, that means you maybe need the higher pressure ratio of the compressor in order to increase the pressure to the desired value. Okay. Alright, so we try to look into the example. So example 3.7. So I hope you can understand the short explanation. Okay, but on top of that, the regeneration basically is a method that we to increase the value of the thermal efficiency. Okay, so you reduce the value of heat addition, and then you get the Q save, and then the hot gases has been achieved the higher temperature, entering the combustion chamber, almost similar with the hot gases temperature that leaving the turbine. Okay, right. But of course, they have some losses. Okay, when through the regeneration, that particular regenerator. Alright, so we go for the example 3.7. So a Brayton cycle with regeneration using air as a working fluid has a pressure ratio of 7. Okay, the minimum and maximum of temperature of cycle is 310 Kelvin and 1150 Kelvin. So this one is going to be T minimum. So this one is going to be T1 and this one is going to be T3. Okay. Right. So it's T3. Okay. So here is T3. Okay. Right. Sorry. T3. And then assuming entropy efficiency 75% for the compressor and 82% for the turbine and effectiveness of 85% for the regenerator, you have determined of the air temperature at the turbine exit, network output, and the thermal efficiency. Okay, right. So as when you refer to my previous slide, so I prefer to start the calculation with the TS diagram, and then you find out the properties at each state before you answer the question. Okay, so we start the answer with the TS diagram. So this is the TS diagram. Okay, in this case, so the TS diagram. So here is the temperature curve, right? 1, 2, 3, 4. As long so since they have the value of the isentropic efficiency, so that means it's going to be the isentropic, and then you have the value of T2 actual, and then as well as the turbine. Okay, and then they have the regeneration. So from the T4A, we have the state 5. So here is 5 prime, and then you have the 5 here because this ratio will create the effectiveness of the regeneration. Right, so in this case, the value of RP is given, which is P2 over P1, which is 7 in this case. Okay, settle. And then they give you the value of T1. So T1 is given by 310 Kelvin. Okay. And then at the same time, they give you the value of T maximum, which is in this case is 1150 Kelvin. Okay, right. And then they give you the value of centropic efficiency for the compressor, which is in this case will be 75%. Okay. And then they also give you the value of isentropic efficiency for the turbine, which is in this case is 82%. Okay. Nevertheless, they also give you the effectiveness of regenerator, which is in this case is 65%. So you got all the information, and then the TS diagram is ready. Then you can proceed to calculate the parameter at each state. Start with state 1. Okay. Start with state 1. State 1 is give you the value of T1, so it's okay. So 310 Kelvin, right? So you're done for the state 1. And then you go for the state 2. State 2 is a isentropic compression. Okay. Right? So in this case, you can use isentropic relationship T2S over P1 equal to P2 over P1 K minus 1 divided by K. So this one is RP K minus 1 divided by K. So T2S actually is equal to T1 310. Here is 7. 1.4 minus 1 divided by 1.4. So you get the value of T2S actually is equal to 540.528. Okay. 540.528 Kelvin. Okay guys, now you have to search for the value of T2 actual. So by using the formulation of isentropic efficiency for the compressor, which is in this case is W ideal divided by W actual. Okay, in this case which is M dot Cp T2S minus T1 divided by M dot Cp T2 actual minus T1. So this one can be cancelled out. Okay, and then they will left you in terms of the temperature. So T2S is 540.528. T1 is given 310 divided by the T2 actual minus 310. So from here, you will get the value of T2 actual, which is in this case is 617.3708. Okay, guys. Okay. So you solve for this one, and then you can proceed to state 3. Okay. So state 3 actually is a process of constant pressure heat addition. Okay. So T3 is given, which is 1150 Kelvin. Okay. Right. So you're done for this state 3. And then you go for the state 4. State 4 is isentropic expansion. So you can use isentropic relationship, which is T3 over T4S equal to P3 over P4, K minus 1 divided by K, and then also is equal to P2 over P1, K minus 1 divided by K, also equal to RP, K minus 1 divided by K. So T4S can be determined by T3 is 1150 divided by the RP is 7, 1.4 minus 1 divided by 1.4. So eventually you will get the value of T4S is equal to 659.5402. Okay, guys. Here this one is 0. Alright. And then similarly for the state 2, you have to find the value of T4 actual by using the isentropic efficiency for the turbine, which is in this case is W actual divided by W ideal. Okay. This case is M dot Cp T3 minus T3 minus T4 actual divided by M dot Cp T3 minus T4S. Okay, so you can cancel out this M dot Cp. Then you can put the values. So here is 0.82, and then T3 is equal to 1150. T4A actually the parameter that you want to search 1150. T4S is 659.5402. Okay, guys. So you get the value of T4 actual, which is in this case is 747.8224. Okay, 8229. Sorry, 8229 Kelvin. Okay, guys. And then don't forget you have the regenerator state. So that means this is state 5. So for the state 5 is regeneration. Okay. So T5 prime actually is equal to T4 actual, which is 747.8229 Kelvin. Okay, solve this one, and then you can find the value of T5. So T5 basically you can use it as the effectiveness of regenerator, which is in this case is determined by the Q regen actual divided by Q regen maximum. Okay, so this one basically is M dot Cp. Q regeneration is T5 minus T 2 actual divided by the M dot Cp T5 prime, okay, minus T2 actual. So this one you can cancel this one. Sorry. Okay, so this one is here. Okay, sorry. Alright, guys. So you can cancel this thing out. Okay, M dot Cp. Okay, so you can put the values. Okay, so here is 0.65 equal to T5 minus T2 actual. So T2 actual is equal to 617.3708. Okay, so T5 prime actually is equal to 747.8229 minus 617.3708. Okay, so from here you get the value of T5 actual, which is T5, not T5 actual. Again, guys. Okay, so T5. Okay, so T5 here. Okay, is equal to 702. 702.1647. 1647 Kelvin. Alright guys, you find all the properties that is state, and now you start answering the question. The first question is, you want to calculate the value of the temperature that exit the turbine. So that means this one is T for actual. So T for actual, you already calculated, which is 747.8229. Okay, you solve for this. And then question number 2, they require you to calculate the value of W net. So W net, okay, so W net actually is W turbine minus W compressor. So you have to calculate the value of W compressor first. M dot Cp, T2 actual minus T1. So Cp, T2 actual minus T1. Put the values 1.005. And T2 actual actually is equal to 540, okay, 528, okay, you already calculated. And then T1 is given, which is 310, okay. Then you get the value of W compressor approximately is 308.9077, okay. Alright guys. And then you can proceed to calculate W turbine, which is M dot Cp T3 minus T4 actual. So in this case is Cp T3 minus T4 actual. So in this case is 1.005. T3 is 1150. T4 actual already calculated, which is in this case is 747. Okay. 0.8229. Okay. So that means here is the blue turbine is equal to 404.1879. Okay guys, now you can calculate W net by simply W turbine minus W compressor. Okay. In this case is 404.1879 minus 308.9077. Here we get the value of W net is 95. Okay. 0.281. Okay. Okay guys. Alright, so we get the value of W net. Okay, and then you can proceed to question number 3, which is require you to calculate the value of thermal efficiency. Thermal efficiency is W net over QE. So W net already calculated. Okay, so no problem. So W net is 95.281 kilojoule per kg. So already calculate this one. Then you have to find the value of Q in. So Q in actually is equal to M dot Cp T3 minus T5. So don't forget, when you have the regeneration, that means the QE is between the temperature at inlet of the turbine minus the temperature that inlet of the regenerated. So here is, since m dot is not given, so just left with T, T3 minus T5. So you put the values. So T3 is 1150 minus T5. So T5 actually is equal to T4 actual, 747.8229. So from here you will get the value of Q in is 450.0745 kilojoule per kg. Okay, right. So from here you can calculate the thermal efficiency. Is 95.281 divided by 540.07545. So you get the value of thermal efficiency is 0.2112. Okay. Alright. Alright. So I hope you understand this one. Okay. So you answer all the questions. And now before we end, let's try to solve the example for 3.8. So air enters the compressor of the regenerative turbine engine at the 100 kilopascal and 300 Kelvin. So that means air enters the compressor. The keyword here just means it's going to be, this one is T1 and this one is T1 and it's compressed to 800 kilopascal. So that means this one to be P2. Okay. The generator has the effectiveness of 85%. And then the air is entered the turbine at 1200 Kelvin. This one is going to be T3. Okay. This one is going to be T3. Right? And then for the compressor efficiency of 75% and turbine efficiency of 86%, determine the heat transfer in the generator, the backwork ratio, and the cycle thermal efficiency. Right. So, okay. So, I'm sorry. We need some space to solve this one. Sorry. Okay. Right. Okay. Right, guys. So you have this one. So start your calculation with the TF diagram. Okay. So always start your your solution with the TF diagram. TF diagram. So here is going to be the temperature curve. 1, 2, 3, 4, and then you have the actual values because of the isentropic efficiency for the compressor, and also as well as the turbine. So from here you have the state 5 prime, and here is state 5. So in this problem, they give you the value of P1. So P1 is given, which is 100 kilopascal. Okay. And then the value of P1 also given, which is 300 Kelvin. Okay. Alright. So you get those properties. Okay. And then the value of P2 is given also 800 kilopascal. So basically from here you will get the value of pressure ratio, right? And then the value give you the value of effectiveness of the regeneration. In this case is 85%. Okay. And then they also give you the value of T3, T maximum. So T3 equal to 1200 Kelvin. Okay. And then they also give you the value of isentropic efficiency for the compressor. Compressor, which is in this case will be 75%. Okay. And then they also give you the value of isentropic efficiency for the turbine, which is in this case 86%. Okay. So you have to do state by state. Start with state 1. P1 is given by 100 kilopascal, and T1 also given by 300 Kelvin. Okay, you solve this one. And then you go for the state 2. It's a process of isentropic compression. Okay, you can use isentropic relationship. Okay, P2 over P1, K minus 1 divided by K. So T2S actually is T1 is 300 Kelvin. Is P2 over P1. So P2 is 800 kilopascal and 1 is 100 kilopascal. 1.4 minus 1 divided by 1.4. So from here you will get the value of T2S will be equal to 543.4342. 4342 Kelvin. Right. And then you can search for the value of T2 actual by using the isentropic efficiency for the compressor, which is in this case is W ideal divided by W actual. Which in this case is M dot Cp T2S minus T1 divided by M dot Cp T2 actual minus T1. So this one can be cancelled out. So you can put the values. So isentropic efficiency for the compressor is 0.75. T2S actually is equal to 543.4342 minus T1. So T1 is 300 Kelvin divided by the T2 actual minus 300 Kelvin. So from here you can get the value of T2 actual, which is in this case 624.5789. Okay. So guys, you solve for this one. Okay. And then you can proceed to state 3. Okay. State 3 is the process of constant pressure heat addition. Okay. So we see T3 here is given by 1200 Kelvin. Okay. So no problem. Get this one. Okay. And then you can proceed to state 4. Okay. We go for the state 4. State 4 is a isentropic expansion. Okay. So isentropic expansion, you can use isentropic relationship, which is T3 divided by P4S is equal to P3 over P4, K minus 1 divided by K, and this one is equal to P2 over P1 powered by K minus 1 divided by K. So from here, you get the value of T4S, which is in this case 1200. P2 is 800 divided by 100. 1.4 minus 1 divided by 1.4. So you get the value of T4S actually is equal to 662. 662.4537. 4537 Kelvin. So you got all these terms. Okay, you got all these terms. And then you go for the isentropic efficiency for the turbine in order to find the value of T4 actual. So here is W actual divided by W ideal is M dot Cp T3 minus T4 actual divided by M dot Cp T3 minus T4S. So here it can be cancelled out. So you left your equation in terms of the temperature. So you put the values. So here is 0.86. T3 is equal to 1200 Kelvin minus T4 actual divided by 1200 minus T4S. So T4S actually is equal to 662.4537. So from here you will get the value of T4 actual, which is in this case is 737. 0.7102. So theoretically, basically the T4A actual will be higher than T4 ideal. You also can be proven at the TS diagram. Right, so now we go for the state 5. Okay, so state 5. state 5 actually at the state where regeneration has been take place. So T5 prime is equal to T4 actual, which is 737.7102 Kelvin. Okay, right? And then you go for the uh, T5. So T5, so you use as the regeneration effectiveness. So we have here is Q regen actual divided by Q regeneration maximum. This P here is T5, okay, minus T2 actual divided by M dot Cp T5 prime minus T2 actual. So this one can be cancelled out. Then you apply the values. So 0.65 equal to T5. So T5 here is the parameter that you want to search. Okay. Okay. So T5 minus T2 actual. T2 actual is 624.5789 divided by T5 prime, which is 737.7102 minus 624.5789. So now you find the value of T5, which is in this case is equal to 698.1142. Okay. Alright guys, to find out the parameter at each state. Now you start answering the question. So the first question is, they want you to calculate the value of Q regeneration. Q regen is M dot Cp T5. T5 minus T2 actual. So here is Cp T5 minus T2 actual. So here is 1.005. T5 actually is equal to 698.1142. Okay. T2 actual is 624.5789. So from here you get the value of Q regeneration, which is this case is 73.903. Okay. Kilojoule per kg. And then the second question is, they require you to calculate backwork ratio. So backwork ratio actually the ratio between W compressor and compressor work and the turbine work. So calculate a W compressor is M dot Cp T2 actual minus T1. So Cp T2 minus T1. So 1.005. T2 actual is 624. Okay. 0.5789. Okay. Minus the T1. So T1 actually is equal to 300 Kelvin. So from here you get the value of W compressor, which is 326. 0.2018 kilojoule per kg. Alright guys. And then you proceed to calculate W turbine, which is M dot Cp T3 minus T4 actual. So here is Cp T3 minus T4 actual. So here is 1.005. T3 is equal to 4,200. Okay. T4 actual actually is equal to 737.7102. So W turbine eventually we get 464.6013. Okay guys. Then you can proceed to calculate backwork ratio, which is W compressor. divided by W turbine, which is 326.2018 divided by 464.6013. So backward ratio actually is equal to 0.702. Okay guys. Now you go for the last question, question number 3. So the last question required you to calculate the thermal efficiency. So W net over Q in. The W net just simply W turbine minus W compressor, which in this case is 464.6013 minus 326.2018. So W W net actually is equal to 138.3994 kilojoule per kg. Then you can proceed to calculate the value of Q in is equal to m dot Cp T3 minus T5. So since that give the value of mass flow rate, so T3 minus T5 1.005. So T3 actually is equal to given 1200 minus T5. So T5 actually is equal to 698.1142. Okay. Right. So 1142. Then you get the value of Q in actually is equal to 504.3952 kilojoule per kg. Then you can proceed to calculate the value of thermal efficiency, which is 138.3994 divided by 504.3952. So you get the value of thermal efficiency is equal to 0.702. Quite high, right? Alright guys. Okay. Sorry, it's not sorry. This is not the answer. This is a backward ratio. Sorry. So the value of the thermal efficiency actually is equal to let me check again. Thermal efficiency actually is equal to 0.274. Okay, 0.274. Okay, guys. I think I hope that all of you understand what I tried to say, and then I also show you some example how to solve the problem related to the regeneration. Well, I think for the chapter 3 will be ended here. So thank you very much for your attention, and I hope that all the material in this presentation will be useful for you to understand about the basic calculation for the gas turbine cycle. Alright guys, see you again. Okay, thank you very much for your attention and have a nice day. Thank you very much.